Hello everyone and welcome to the next Chat Physics Q&A. Today we have James De Winter here, and given that my voice isn't the best today, I'm going to pass straight over. Hello James, could you tell us a little bit about yourself?
Hi, yes, my name's James. I'm a physics teacher. I trained to be a physics teacher back in the early 90s and taught in secondary schools around Cambridgeshire and Suffolk. And then I guess for the last 15 years or so, I've worked at the Faculty of Education at the University of Cambridge, running the secondary PGCE teacher education course, working with biologists and chemists and primary teachers as well. I also work for the Ogden Trust, doing various things, predominantly supporting early career teachers. And in my spare time, I'm also a member of a research group in Sweden, trying to check if I'm doing the other two things properly.
Excellent. So we're here today to talk about this book. I'll show you guys really quickly. This is Teaching Secondary Physics. I know that's not quite zooming in just there. So James, tell us, the first edition for this came out in like 1999 and the second edition in 2011. What is it that you think's been updated in this third edition to give us an idea of the importance of this book?
Well, we got carried away and we virtually rewrote the whole thing. So just to be clear, although I've written some of the chapters, I co-edited it with Mark Hardman from the IOE, and there's a whole collection of authors who wrote individual chapters, but along the main physics themes of, forces and electricity. So we took the existing book, and although some of the original thinking in the previous edition is there, we virtually rewrote most of the chapters either partially or pretty significantly. So I would say it's an almost complete update in terms of that. It's supposed to be a kind of core how to be a physics teacher book, put together with the Association of Science Education. So we had their kind of eye from an editorial point of view. So in the simplest sense, if you've got to buy one book about telling you how to be a secondary school physics teacher, then this is at least what this book is trying to do across the main topics.
Love it. So what do you think has led to this sort of need to rewrite? Do you think it's more like teaching strategies or content or perspective? What is it in your opinion that's really
it's kind of hard to know, because in a way, I don't want to offend too many people, the physics we teach hasn't really changed much in high school since 1915 odd. There's no quantum physics in there. I think there are some issues about activities, technology, things like that. But I think the way we see how physics might be taught and approaches just kind of evolves over time. I always think, that there's something healthy about accepting that our understanding of the best ways to teach things will change over time. And I would hope, maybe I'll be involved, maybe I won't, depends how long it takes, that maybe not in 2 years, but in 10, 15 years, we'll want to revise it again. But I think also, in addition to that, I think there are other things that became more important that perhaps weren't as addressed. So we were interested in trying to push some more careers and contextual fitting to some of the things in there, more real world applications, trying to draw from a wider range of science examples that we were using, or contextual examples to, when I say make it more inclusive, that's a challenging thing to do, but I think we tried to draw in some of those issues. So it's not just, white European men from the last 50 years that are mentioned, or 200 years.
Oh, yeah, that's really good to know. And I think things like careers and the sort of contextual sort of applications of all this can actually change quite rapidly. And you never know how short a time frame it's going to be until we need to revisit and we need to look at where this knowledge is actually being applied nowadays. And we had a really lovely chat. So my year 12s were talking to, I think it was Oxford University perhaps, and it was about studying and it was about physics. And one of the things they said was actually about how important it is to look at the boundaries between subjects, because that's where so many of the sort of developments sort of begin at those boundaries. That's where the origin of some ideas comes in. So yeah, being able to revisit these and think about what's appropriate nowadays is so useful for our young people going forwards. And is that something that you intend for staff or teachers to be able to use regarding sort of a little bit of knowledge of careers and context?
Well, it's an impossible challenge in a book, to write 30, 40, 50 pages on how to teach forces. So the kind of tension that sits within what you're trying to do. I think at the heart of it, we're not offering a scheme of work.
Yeah.
We put together a kind of, in each chapter, a progression narrative in which the ways we think ideas should be taught. And then around that, suggesting stories, illustrations, careers thing, mathematical issues, language issues. These are things that become important in terms of physics teachers. So it's a very difficult balance to strike. And what I would also say, which maybe I didn't mention earlier, is that we were very conscious when writing it that there are probably likely to be more people without a physics degree reading this book than with a physics or engineering degree.
Yeah.
And whilst we still hope and have aimed, the author team to write for those, we're aware that we needed to support and shore up and give some of that confidence to, out of field teachers who are being asked to teach physics. The core physics engineering degree physics teachers, we love them. They're beautiful people. We want to support them. But we all know, with the shortage of physics teachers, that there's a large kind of constituency of out of field teachers who need kind of the security of a kind of considered position on how we might approach that. And indeed also some of that stuff that sits around the edge, some of those stories, some of those contextual examples, just to fill out their lessons so they don't feel they've got to just deliver the curriculum. Horrible phrase, but if you don't feel comfortable in your subject knowledge, where do you go for those other things? And interestingly, maybe skipping ahead, we've got resources within physics. Richard Brock, who's involved in one of the chapters, he's written his wonderful stories from physics booklets from the IOP, and there's another example of that richness that we want people who are teaching physics to bring into their lessons.
Yeah, absolutely. I really love the start of the book where it says, "What is physics?" It's such a great opening. We've got lovely phrases like the explanations of phenomena, how to see complex and sometimes abstract ideas. What's physics to you, James?
Oh, who knows? Looking at the world going, wow, and then trying to ask a bit more about it. I mean, I just think, what I love about physics is it enhances the majesty of the natural world. I look at things, I go, oh my God, that's amazing. Whether it's, a plastic bird balancing on my finger or a light bulb lighting up. And what physics does is just gives a richness to that in more detail. It's a challenge. I mean, that particular section about what is physics, Mark and I were arguing for months about what the answer is, because I'm not quite sure we know. And there's an interesting point on that, actually, that sometimes physics can offer a rich description of what happens in the world, and sometimes it can offer an explanation, and sometimes it can offer both, but sometimes it can't. And actually being comfortable with I can describe the kind of the what, but I may not have an answer to all the why questions. We've tried to touch on some of those things in the opening chapter, as well as just some straightforward, here's some tips about how to be a good physics teacher. Because it is, natural philosophy historically. I know, you think, oh, well, I can't teach that to 14-year-olds. Well, you can't spend all the time on that, but there is an element that we're living in an imagined world. And physics is interesting in the sense that at school you would teach Newtonian physics, or you would teach a simplified model of how electric current worked, but at university you'd learn a whole different model, and we just need to stick with that and not say it's right or wrong. I don't think I've answered your question, but I'll stick with the world's amazing. I go, wow, and I want to know a little bit more about what makes that wow happen.
Yeah, definitely. Had a comment from Gethin. Thank you, Gethin. It's so nice that you're here. Physics is a study of matter and energy, written by Hawking. He says that's his go-to definition. Do you know what?
That's fine, as long as no one asks you to define energy, and then you'll get into a real can of worms.
Absolutely. I think that's my definition when I'm tired or fed up, perhaps, and I just need to get that answer out of something that's just going to give somebody poised thought and go, oh, okay. But as you say, there's so much more from that.
It's a study of the world and stuff happening in the world.
Yeah,
and that's why it's so beautiful, really, because we get to study everything. There's nothing's off limits, really, which is, I think, both constraining and enabling, depending on what class you've got.
Yeah, I must say though, I remember one of my funniest memories from school is when I had a year 7 class, and I sort of introduced myself as the head of physics, and one of the students sort of sighed, which was heartbreaking, and then another just sort of went, what is physics anyway? And I was just like, well, everything. I was like, everything's related to physics. And we ended up spending, and I don't regret this even to this day, it's probably not what I should have been doing. It was on the curriculum. I probably spent 30 to 40 minutes, and they would throw something at me that they thought had nothing to do with physics. And I would tell them everything I could about why it related to physics. And my little phrase at the end of everything was physics, bang. And then every time I saw those year sevens in the corridor, they would shout as loud as they can, physics, bang. And we just got so many head turns from the other members of staff. But it was just so nice having this little group that absolutely love those, love to be challenged and, like you said earlier, think differently. So,
but it's interesting, the world is just endlessly fascinating. We see things that go, oh my word, and what science and physics does is just give us the tool to look a bit more deeply. And I think, if I might be skipping ahead, but one of the things that concerns me a bit about some of the movements in physics teaching is that it can become too obsessed with mathematical calculations. And well, what's that about? That's to tell me something about something amazing in the world. So you can detach from the real world with the kind of calculations bit. And I think awe and wonder, that we're not party entertainers, but we don't need to be, because all the cool things can be explained with physics. So we can be party entertainers and physics teachers at the same time. And as long as we're doing both, then I'm happy. So
I think we've kind of got it all there, haven't we? Now, the next part of the book is actually about a short piece on doing physics, and we've talked about the awe and wonder. Do you think physics ever suffers a little bit from being largely quite abstract in terms of the learners and the people who engage with it?
Yeah, that's almost impossible question for me to answer quickly, so I won't. I'll sidestep and answer a different question. I think the abstract nature of physics is challenging for students, and I think it can be for some students what stops them from kind of making a connection with it, because they can't see what it's about. It's operating this imagined world. And I do think that one of the challenges and joys of being a physics teacher is to build the bridge between the real and the imagined. If we think about doing physics as in what are physicists doing, the challenge there when we're talking about students is that a lot of that is highly abstracted and highly mathematical. To be successful in a physics degree, and certainly kind of doctorally and beyond, you move more and more away from the real intangible world and operate in multi-dimensional geometry and what have you. And so there's a challenge there between what physicists are doing, and there's a kind of related challenge about the relationship between physics and engineering, and where that goes to, because there are going to be many more engineers than physicists. So who are we trying to do to support? So I think it's a challenge to connect what physicists are doing and what is happening in the classroom for students. But I would always try and root it back to the real and tangible phenomena, the Hawking and Jones's kind of matter and energy, because I think it's easier for us because we can operate in a real imagined world, because we've been thinking about physics for 10, 20, 30 years. But when you're 15, it's kind of harder. And part of our job is to join those together.
Yeah, definitely. I think as well, sometimes we almost suffer again with our learners from the idea that we teach them quite isolated bits of physics bit at a time. And I don't know about you, but we find quite often that, particularly at A level, they probably really struggle quite a lot through year 12 if we talk about sort of the average learner. And it's actually as we get close to the end of the course, when you can relate everything back to the original learning and you go back to basics and you start to make more connections, that they actually make quite rapid progress once they see more of the whole story. Is this something that you find? Do you think that explains it?
Yes, I mean, it's interesting that as you said that, I had a flashback to doing my A-level physics exam in 1980 something or other, but where I think March, April in the upper six, I suddenly all made sense, and I could see how gravity and fields and things join together. And I think there's a danger in expecting our students to get there that quickly.
Yes.
Because I think you just need to accumulate some foundational building blocks before you can, you cut. if you're kind of secure in your understanding of gravitational fields, and you're secure in your understanding of electrostatic fields, you can then go, oh, this is 1 over r squared, and then it's 1 over minus, and you can see that actually what you've got is a kind of field thinking.
Yeah.
But that sort of can only really come, this is the whole expert novice thing, that can only really come when you've got the foundations in both those areas to enable them to join up. And if you just say, oh, well, gravity and fields are the same, gravity and electrostatic fields are the same, it's okay on a surface level, but actually if I don't really understand much about gravity and I don't really understand about electrostatic fields, I can't, it just becomes two things I don't understand, allegedly similar. So there's a real tension between where it happens. And I think, 15 years ago, the A-levels were very modular, and I think that encouraged very kind of compartmentalized thinking for students. And that was I'm just in one mode. I only care about mechanics.
Yeah.
And so I think that kind of, when the synoptic elements and those questions come in, is more helpful. But I think we also have to be sympathetic to how much we can expect, whether it's at school level, GCSE and A or post 16. We can see it's all joined up. We can grand unified theoryify and say, well, it's all right. It's this quantum and gravity, and we'll worry about that. But that's because we've been worrying about that or thinking about that. So I sometimes think you have to kind of hold our nerve about when we're realistically expecting students to join those things up. We should be throwing the lines and talking about the connections, but we have to be realistic about the meaningfulness of the connections that your average 14 or 16-year-old is going to make. And in fact, just understanding what's going on inside a wire that turns everything on, that's an interesting thing. I don't need to worry that it's really explained by fields. Well, no, just have this model. It's fine. It's sufficient for understanding what's going on.
Yeah, that's it.
So I kind of think there's a sort of patience one has to have. Because, I still struggle with some of these things. I'm still going, I'm not quite sure about. So, and I've been worrying about physics teaching for 25 years. So it's not really fair to be annoyed with a 15-year-old for not quite joining it all up. Absolutely. But we should try. I'm not saying we shouldn't try.
Yeah. I try to take the encouraging, and I don't know if it's just an encouraging approach, but it's like, but it will come. We will get there. Let's not worry about the fact that this doesn't all make sense right now. Let's learn a little bit more and see if we can connect it. I think sometimes, particularly as teachers in schools, we have this idea that we have to nail everything and nail it really, really good before we move on. But sometimes moving on and telling more of a whole story can support the thinking and the learning so much more. It's trying to find a balance between being good enough at that point in time and actually providing enough for them to think widely, to actually understand it in a way, a way that they can make these connections for themselves and make them make sense.
Yeah, so. And this is all a kind of compromise. But I mean, on that point, what would also say is that I rarely get angry and finger pointy. But one of the things that really annoys me when some teachers say is when they kind of go, "Oh, well, what I taught you last year was wrong. This is the correct one." I think that's a really unhelpful way to look at physics, and it's really demoralising for students who are on exactly that journey that you're talking about. Yeah. Because what we're really doing, I mean, none of it's right. None of the school stuff's right. I mean, we teach, things don't fall. It's all curved space time. But we don't tell them that when they get to university. But actually what we're doing is we're providing a model, and this goes back to the kind of wow of the universe. We're providing a model that provides some level of meaning in a phenomena they can see. And so I'm happy I don't see it as a compromise. I just see it as part of, what to me learning physics is about, what I want for students. Yeah. And there are some things that we just don't tell them. I don't know, in 15 years in the classroom and even now, no one ever said to me, if all those protons are in the middle of the nucleus, sir, why don't they push apart? You told me positive. No one ever asked me that.
No, I've never had it asked.
Tell them about the strong force because I probably don't want to tell a 14-year-old strong force. But so I'm kind of, I take a more relaxed approach about what is right, because I just think it's about getting better and getting a richer understanding of the world, and also, and I do think this is important. Sometimes, at a certain level, physics will provide a wonderful description, but we may not be able to get into the reasons why at a certain point, which is intellectually frustrating for some and might be intellectually frustrating for the teacher. But there's always a pragmatic kind of angle that situates in the classroom. Absolutely. Because I could spend 5 lessons talking about curved space-time, and most of you will get confused. Probably I'll get confused as well, and we won't actually get where I want you to go, which is just to know that when you drop two things, if you take away air resistance, they're going to accelerate at the same rate, which is a kind of cool thing about, you know, billiard balls and bricks and elephants falling off a Tower of Pisa. It's an unexpected thing, and I'm happy to kind of revel in that unexpected thing before I talk about, you know, LIGO and
of course,
space-time curvature bending through the universe because of black holes.
Definitely. Let's get into some of the content of the book. So early on in the forces topic, you mentioned the idea of force glasses. Why do you use this term, and what do you really mean by this?
So there's a problem, right? The problem in teaching forces is what is a force? Can you see it, right? And it's, so you're dealing in an abstracted model. We cannot see forces. They're not real. They're a kind of philosophical construct. We can see motion. And if you're going to talk about forces, I think you need to at least acknowledge to some extent that you're living in a slightly different way of looking at the world. So the point of the forces glasses, which, you know, well, forces spectacles, depending on how posh you want to be. I mean, I didn't come up with them. They've been in the IOP thing. I think Phil Scott and people at Leeds a long time ago talked about them. In one sense, it's a piece of teaching theatre. You have a pair of glasses with a big forces on, and you're saying, I'm going to put my forces glasses on, and when I look at the world, these rules apply. You know, but that is one way to acknowledge to students that we're dealing in an abstract world. And certainly from the way I teach it and the way I wrote that chapter, different people work in different ways. What I also like about it is that with the forces glasses on, as a student, I have fewer open what's happening, what's going on questions. I have a set of rules. If it's speeding up, some forces are unbalanced. If it's, you know, and all that, you know, which is really it's my kind of, you know, I'm just repackaging Newton's laws. But rather than saying to a student, oh, well, what's going to go on? I put my forces glasses on. I look at the world in a particular way, and I have a set of rules that I will trust that will always work. I can learn those rules, and I can consistently apply them to any situation. The forces are unbalanced. Not what will happen. Pick, speed up, slow down, change direction, right? The forces are unbalanced. Sorry, the forces are balanced. Pick, carry on at a constant speed in a straight line or stationary. And so I think it makes it easier for the students because there's a set of rules. And of course, that is actually a manifestation of how physics works. So although I wouldn't get into this necessarily with students, I might talk to teachers about it. That is how physicists look at the world. They decide to put their forces glasses on today. They might put their energy glasses on another day. And when they do, there's a whole bunch of assumptions and rules that are just taken as read that apply. You know, the law of conservation of energy would be one that might be, or mass energy, depending on who you're working with. And so what I like the forces glasses, one, because I'm a bit of a kind of show-off teacher. No one has to be like me. That would be a horrible thought. But there's an element of that. But there's a more significant thing like the nature of physics. And back to that real and imaginary thing. You know, what is a force? I don't know. We just made it up to explain stuff. It's not a thing like a table is a thing, or a drop ball is a thing.
Yeah.
And so the forces glasses, as I said, are a way to acknowledge that, but also are a way to provide more certainty and security to students, and indeed perhaps to teachers, because non-Newtonian thinking is not, you know, the exclusive remit of 14-year-olds. I've met a lot of people with degrees from good universities who think a ball in the air has got a forward force acting on it. And so I just think for me, it helps. So there's a problem, abstract nature of forces. And then in the book, I'm offering a solution, which is to have the forces glasses. Whether you wear them or not, I guess, is up to you and how you want to do that. But really, that's what physicists are wearing, those glasses all the time. And the really good physicists looking at a problem go, which glasses should I wear today? Oh, I think I start with my momentum glasses. I got nowhere. I'm going to put them off and put my, you know, angular, you know, whatever. I think that's how physicists wear.
Yeah, definitely. And it's such a nice approach to have to problems as well. I think it really unlocks the idea to students that you can't look at every problem with the same perspective, and you can't look at every problem with the same set of assumptions. And if we did, we probably wouldn't be where we are in the physics understanding today. So it's definitely a good way of making them think about different perspectives and what they are, essentially which assumptions they are focusing on. I really like in the key activity that you mentioned during the forces topic, which I think you had put a lot of work into the forces topic. That was one of yours.
Couldn't let anyone else write it. It was just, I decided, no, I'm going to have to do it.
I really like the way that you suggest very heavily that the equation relating force and extension should be something that students are supported to think about, consider, and essentially work out for themselves. So it's the idea that you are looking at data, you are looking at the relationship and using this to try to draw together that equation. Do you think this is done well in schools? I would suggest that with potentially the lack of experienced physics teachers, maybe this has fallen off the radar a little bit, and I know that I'd like to see a lot more of it. So what are your thoughts?
I'm not going to pass judgment on classrooms because I haven't been, watching it. But I think you're right. I think what happens is if you don't have a clear why are we doing this, it's very easy to book lesson P 4.1, get the tray with the springs and masses and graph paper, and perform that activity. And successfully in the sense that the students will get a graph. Yeah. And what I think is a shame is it's not about the spring, right? The reason we do the spring is because the spring is the thing that we can buy mass produced, easy to set up, that provides absolutely perfect, reliable results within the range of masses we've got available, right? What that lesson is about is, hey, for a certain bunch of materials, there is a stretchiness pattern that is universal. I can take a piece of steel, stretch it in a lab, and I can just project that pattern into building a suspension bridge with a piece of steel I've never made that length and know it will happen. So I think what happens is that the danger, the thing you kind of alluded to, is that sometimes people just do the Hooke's law thing, collect the results, draw a graph. And I think what would be sitting behind that is why do I traumatize the teachers I work with by saying you've got to imagine me at the back of every single lesson going, Miss, Sir, what's the point of this lesson? Because actually, if you haven't got an answer, you need to do a bit of thinking.
Absolutely.
And so there's a stretchiness rule about materials, not all of them, but a lot of them, whether it be bone or strawberry laces or springs. And we're going to do with springs. Because, I mean, so this is where I think the other examples we use are really powerful. So fine, we're going to do springs, but then talk about, I mean, I sometimes suggest you squash, you stretch strawberry laces, you get reasonable results. You squash marshmallows, that's great because that rule works for squashiness as well as stretchiness, but it also works for bones. So if you pick your other examples, like if you're a human pyramid and bone has a stretchiness for how much, it's back to this wonder of the world. So I think what can happen is that you can get fixated on the equation and the performance of the graph, which is important and the students need to know. So I'm not going to throw that aside. But actually, the cool thing is that I do a little bit of an experiment here, and then I know what will happen with the thing. I can throw my physics into the future, and I know what the answer will be. And that's kind of really cool because, I mean, I've got the spring in the lab. I don't need to know anything about a spring. But if I can use that to imagine, well, that's how a shock absorber will work, and whatever it may be, I just think is the bit, and that doesn't need a lot of work from the teacher. You don't have to. You still, it's a required practical. We just have to. Everyone's going to stretch springs, whether it's exciting or boring. Just we've got to do what we're told. But what we can do is to tell the students, oh, this is really important because the same idea is used with skyscrapers, and how squashed, I need to know the foundations, what they can take, and in fact they're going to get shorter, because if I don't account for that, the compressive tension, then my skyscraper is going to sit, the front door, the lobby is going to be 30 centimeters too low because all the, it's there. So I think we got to do the core rules. There's a job to be done. I can't just make physics beautiful and wonderful. But the problem is I can do that around the edges of stretching springs. I don't need to kind of derail my compliance with QCA or whoever telling me what I can do that as well.
Yeah. So I did this experiment the other day or core practical, as we should probably call it nowadays. But I gave them the choice of whether they wanted to use springs or elastic bands, because I wanted them to just explore. I wanted them to sort of essentially draw their own conclusions and be able to compare data, and they could have done both. So what do you think the benefit of choosing something like an elastic band or anything else and actually comparing the graphs for the students? How do you think that contributes to that understanding of the usefulness of these sort of given equations?
Well, yes. So we've got what you've just got there is a beautiful aspiration, because what we're doing then is we're saying, oh, well, there's a linear behavior and there's a non-linear behavior. We don't have to talk about hysteresis, but we can have that. The tension, I think, is the kind of classroom mechanics. So if, for example, students are struggling to draw graphs, and we've all been in the room where we gave them 10 minutes to draw the Hooke's law graph and it took them 20 minutes just to label the axes.
Mm-hmm.
So the story you tell is great, and I really like it, and I think the meaningful learning can come from it, that there's a stretchiness, and it might be straight, and it might be curved, and it might be described in one way, it might be described in another, which is how the world works. That there's just a balance then between the pragmatism of getting 13, 14, 15-year-olds to draw graphs. Because what could happen, I'm sure it wouldn't happen in your class, Jinny, but what can happen is that they spend so much time struggling to draw the graph that they don't get to the idea. And that's where it may be, and I don't, I've got to show me the classroom and the students. I'm not going to judge until I see them, but it might be that actually we all do Hooke's law with the spring together initially. Then we can explore other things. But at the very least, we should be looking at these other graphs and say, well, this one's not straight. What does that mean? How might that look differently? Let's talk about that. What does this mean? What, is it harder to stretch or easier to stretch? I know springs and series and parallel probably isn't done to A-level physics, but just actually getting students to hold one spring and pull it. I mean, careful, safety and all that. Don't upset feet. Hold two springs and pull it. You can and put them in series, and you can feel something which would give meaning to that K.
Absolutely.
Because otherwise that K is a stretchiness number, saying how hard or easy it is to stretch. So also, the other thing is that I'd want my spring and my elastic band to be drawn on the same scale, because I've got two things going on. I've got the straight curve thing, but an elastic band's an awful lot easier to stretch. So it's not just straight curve. One's going to be a lot steeper than the other one in its straight and curve. But that's a really rich and interesting discussion that gets to why are we doing this, Miss? We want to understand about stretchy things, because it's important.
I must admit as well, I think one of the reasons that I've done this, and just in case anybody's listening who's thinking, oh no, that's far too much, my students will never cope with that. This is a triple group. It's a group who ask key questions and always want to know more why. And I did feel like it was really well placed in the lesson. And generally their graph work will be reliable enough for them to complete and draw conclusions from. But what I really liked about it is that it really was over to them to pick a material and investigate it, because what we find over and over again is, and I think it's actually come up in some textbooks before, that the topic is actually called springs. And it's just such a shame, because it's not about springs. It's not about springs at all. It's just something we pick because it's easy and reliable to use. But actually exam questions could go out there and get them to apply it to anything really. And students are none the wiser because they've never had that comparison of materials to be able to say, oh, hey, actually, this is a process, this is a method, this is a relationship that can be tested on a whole variety of things. So
absolutely. And back to the book just for a second, what we've tried to do is provide multiple examples, because it's been written about and been researched. One of the things that students do is they think that the phenomena is constrained to the classroom example, or whether it's an experimental one or a given one. So conservation momentum is to do with ice skaters, billiard balls and trucks, and that's it, right? Because they're the only things I've seen. And in fact, one of our jobs as a physics teacher is to say that this is applicable everywhere. This is a universal law. And so, if we take your class, if they're good at drawing graphs and that, then actually it's dead quick to get your curved graph elastic. It takes no time at all. You can do strawberry laces, squash marshmallows, and do a spring in a relatively short space of time. And then you can look at the comparative thing. And then you can say, oh, look, everything has a spring stretchiness, what do you want to call it, elasticity constant. And then look at the comparison. And you're making the point that it's not about springs, it's about the way the world works, which I think is part of our job as physicists. So even if we weren't doing the other experiments, I think it's part of our role as physics teachers and physics educators to say these examples are picked for experimental convenience, but the underlying physics behind it is far more universal. Which is like, I think it's in the first chapter, physics is a universal thing. I get one law here. I can burn a piece of sodium in a room and then look at the lines and then look at a star and go, oh, I know it's got 4.2% sodium. That's amazing. I mean, that's just amazing.
That's absolutely it. Yeah, completely agree. I have not seen, for some strange reason, I've never come across the marshmallow one before, and I'm absolutely gutted that I didn't do it the other day. So I might have to order that this week. I don't know how I've never come across it. I think, I've always been one of those people who, I know this sounds really bad. I'm just going to say it because it's just real life. I try to avoid the use of like food and fun stuff just because I think it takes sometimes they get more focused on the fact that they're playing with marshmallows than what they're actually learning. But I think this is a really good example.
Okay, I'll solve your problem and give you the same experiment, Jinny. Here's the hack, right? And it makes the measurement easy. Just get a sponge, bit of wood, and a big measuring cylinder. Then you can pour in your mass because 1 milliliter is 1 gram, and then you can just measure the height of the board above the sponge. So you can do it that way. But I think it's a fair point about the marshmallows. The reason why I like the marshmallows, actually, and I think this is that it's an experiment that students can do individually.
Yes.
Because there's a lot of people kind of critiquing practical work, and that drives me mad in different ways. But all you need is a marshmallow and 2 plastic cups and some masses, because you just measure the distance between the rims and load the masses into the plastic cup. And so it's very easy to do. And I like that everyone, my class set is, I know we should be using plastic cups anymore, but my class set is accessible. And certainly at A level, because you can find the Young's modulus of a marshmallow. Now, everyone, you've got to do the copper wire, fine, but it takes forever. And, there's a whole class and you've only got one set. So we do that and we learn about how to measure Young's modulus. But then every single person in my A-level physics class, for virtually no cost, is required to measure the Young's modulus of a marshmallow. Has to make some assumptions about the cross-sectional area. Is it slightly tapered or not?
Yeah.
And they can't get away from paying attention themselves because they've got to do it themselves, because I know my equipment is reliable enough. And I cheat, I just don't even need to give them a ruler, just give a piece of graph paper, and that's 1 centimeter squared. It's, So, but the hack for you, if you don't want to give them food, is you can just use a sponge and then a big measuring cylinder, and then you can watch it squash down.
Oh, definitely. I just love these additional ways of doing things to just make it so super clear to them that this is not the only example of this concept. And it's just one of those things that I just really enjoyed reading about, and definitely something to share. You talk about, so actually we've just been talking about compression, but I want to go back to the equation. Do you think we suffer from missing compression because the equation relates to extension? Because it's not something I see a lot, and I worry that we miss out that really important idea.
So I would probably say no, actually, from a pragmatic room full of 14, 15-year-olds reasons. I think let's just deal with stretchiness. And I might do the Young's the squashy marshmallows at key stage 4, but I might save it for A level. I think I would be inclined just to deal with stretchiness. And I think it's part of my kind of expert novice thing about, you and I might know that when you look at the force extension graph between 2 atoms that it is straight, but actually it may, to a lot of students, compression and tension are different things. If you look on an atomic scale, it's not, but in a way. So I think I might, in that particular case, I might not, I might avoid that. And that's, it's a kind of sleight of hand or a limit to the content I'm doing. Yeah. But I think at the expense of, so what matters more to me is that equation has meaning, kind of back to where the question started that I didn't answer. What I want is that K to have meaning and not to be a number. And so if it's a measure of how easy or hard it is to pull the spring, I think that's the fundamental idea I'd want in that lesson. Absolutely. And I might just strip away other things so I can get to that. And so sometimes you just choose not to bring things up because for the majority of, I want everyone to know everything, but
Yeah.
I'm all day, So
there's so much to fit into just a couple of years, isn't there? We really have to strip away the bits that we do feel are not necessarily even misleading, but the things that are going to prevent them from getting to the key point, I guess, a bit more quickly, a bit more simply.
Yeah, and the other thing, if you take that particular experiment, often that's from very early in the student's kind of physics experimental career. And the reason why teachers do it, and rightly so, is that it gets good, reliable results from which to get a straight line. So it makes the first best fit line they draw relatively easy to draw a best fit line. And that may be where I'm actually going to be focusing more on the procedural challenges of the students, of helping them draw graphs, doing a best fit line, finding a gradient, than actually trying to overcomplicate the physics. Because if any experiment has too much procedural stuff about equipment, doing it, and graphs, and too much conceptual, it's just like trying to, well, it doesn't work on phones, but like when you load up 30 apps, your phone slows down, the student's brain.
Yeah, absolutely. So we've got a question here. Looks like Woody's joined us. So James, is the marshmallow inside the cup to stop it falling? Would you like to go through?
So you have a plastic cup. I know they're out of vogue now. So plastic cup from a drinks. Put the marshmallow in the bottom of that cup inside, and then put the next cup inside the other cup on top, so it becomes really stable. So I think hopefully I've explained it really well. I need a whiteboard. The problem is, as a teacher,
I know. Probably should have thought about that. I'm just sitting there going, "Can I get one?" I'm not really sure. But So then we would have two cups stacked inside each other, and then the distance between the two rims can easily be measured. So I was reading about this earlier. It's definitely something that I'm really keen to do a little bit of.
So there's a rubbish drawing, but here we go. That's cup number 1. That's cup number 2. That's the marshmallow, and there's my masses, and I measure the distance between the lips.
Perfect. Thank you so much. Lovely to see a few artistic.
That's not in the book, but there are loads of other really good experiments in the book.
Absolutely, yeah. So, you referred in your book to the ASE's publication, The Language of Mathematics in Science, and this actually came when you were talking about the motion equations that came up. So could you tell us a little bit about what this is? Because it's not something that I've come across. I think I should have. Maybe it'd be something good to share with our audience.
So yes, I mean, the ASE do lots of wonderful things. This particular, I'm afraid I can't give everyone a free copy, but the ASE books on language of mathematics and science are available free. So what happened, Richard Bowen and then Richard Bowen and Richard Needham looked at the mathematical challenges that students faced in science and essentially produced 2 books that were a comprehensive overview of all the challenges students faced, all the mathematical kind of competencies or skills or whatever you want to call them, and then offered an articulation of what the challenges students faced were, and then offered suggestions. And then there's a second book, which has got lots of case studies of what schools and students have done. So I would suggest it's the one place, if you're frustrated about the challenges that the mathematical competency has, that students have with being successful in physics and the barriers and how you might go around them, it's downloadable from the ASE's website. It's a free, both of the booklets, PDFs that we've all, it's not just that they're clever, they've just been given the time to sit and think deeply about that and offer their wisdom in the same way. I'm not suggesting I'm the greatest brain in the world, but I had time to sit down and think about how to teach forces and write it down, and Rachel and Tom and everyone did the other chapters. But those ASE guides are really powerful, and they also have case studies of things schools and students have done. So just one example, there's a thing called transfer, which is where students, and everyone's going to nod and go, I knew this all the time, but I've given it a name, where students are good at a skill in a mathematics lesson and are not good at it in a physics lesson. I can find a gradient in maths, miss, but I can't, right? So like one of the case studies, and it's a small thing, is that the maths department and the science department came up with a kind of graph drawing mat where they just had rules for how to draw graphs, and they used it in both lessons. So they helped signpost for the students, the connection between that. I mean, there are reasons why maths in physics is slightly different from maths in maths, but there's just an example. So those books are fantastic. I mean, I won't rant too long, but I feel that particularly with physics, there's a kind of tension and a problem going on. Physics is mathematical. The mathematical is at the heart of physics, and we can't avoid that. Mm-hmm. But I think there's a danger it becomes too computational. This is Paul Hewitt's book, about this, whereby which we, and more importantly, students, think that physics is about doing sums with numbers. And what part of our job, and maybe it's back to the stretchness equations, we have to make the equations mean something. These are not a hidden number. In maths, A is normally just an unknown number. In physics, A is a measurable, squeezable, squashable, measurable thing. Which is why I hate it. And I don't know any number without units, because the units are what turns the number into a thing. You know, that's why we should be really pedantic about that. Anyway, the ASE book on that, The Language of Mathematics in Science, and I think it's called, like, there's two different names, but you'll find it on the ASE's website. It's just the one-stop shop where Richard have just gone through, catalogued the challenges, offered suggestions, how you might approach it with students. Because we know it's a challenge, and we know it's a barrier for students being successful in physics, and certainly is higher up. And there's a lot of wisdom and thought in that booklet that we've, I've tried to use some of the examples in the forces chapter. I know some of the other authors in the other chapters have done so as well.
Absolutely, that's great. So I know Woody's asking for the guides to be placed in this chat, so we'll have a little look later, see if we can get those links out to make sure people know where to find them. Thank you so much. So I just wanted to move on a little bit to the particles topic, the bit on matter. So what do you think are some of the most common issues with prior experiences that students might have? And how important is it to ensure a sort of continuity of thought? I noticed that you used particle diagrams, some ideas of models, and you also used the chemical formulae with state symbols, which I think is another powerful way of making connections to things that students may already know or may visit later. And it really gets the idea to them that change of state is not a change of substance, it's just a different sort of physical model. So what kind of prior experiences do you think can be problematic?
Well, there's two levels. I mean, obviously solids, liquid, gases are dealt with, and behavior of matter is dealt with in primary education, and often there is some kind of particle model that's involved with that. I think perhaps what changes at secondary school is that particle model is used to explain or connect with the actual behaviors they see. So the misconceptions literature, alternative conceptions literature about the problem is, or the biggest problem is the particle model. And I think it exists on several levels. The first thing I would say, back to the expert and novice, for us as teachers, we have to be very sympathetic that most of us learned that the world is made of particles so long ago, we don't even realize it's a piece of knowledge. If I said, what's this made of? Well, it's plastic. Yeah, James. Well, zoom in, what's it made of? You get to atoms in a heartbeat because you just can't help yourself. It's like what they sometimes call a kind of threshold concept, that once you've got it.
Yeah, absolutely.
So I think seeing that things are made of particles, and I'll be vague in my language of particles for the moment here and upset any chemists, is one of the biggest barriers, and having a kind of effective model of particles, because what starts to happen at secondary school is that we connect the part, why do things expand when they heat up, so we have to then connect the macroscopic observation, expansion, with the micro or submicroscopic observation about particles vibrating more and moving more further apart. So I think a bigger challenge, I know it's not quite the question you asked, but I think a bigger challenge in that is that connection between that model. And that requires a simplification. I mean, when Alan and I were doing that, I had lengthy discussions with chemists and got into arguments in a good way about should they be circular, should they be oval. In fact, we put a thing in the book to say, well, actually, for the purposes of our model, they're circular. Chemists might want to show order and disorder within solids and liquids. So they might want, oval, but we're not going to do that. So I think the challenge there, the biggest challenge, is the connection from the macro to the microscopic or submicroscopic, because you have to join those two things up. And I think it's probably students are not really familiar with putting meaning to the submicroscopic behavior. They might have been told at primary that things are made of particles and they're jiggling around and that kind of stuff, which is fundamental and critical. But I think they're going to have to start to use that at secondary school. Which is why that comes in the chapter. It's conceptually quite difficult, but we put it first because in fact, we start on that and then we go on to some macroscopic stuff. And then the chapter ends with, like, we've done the particles, We've done the macroscopic stuff, extension, whatever. Let's join them up and understand how gases work and the gas law stuff, because you've now got macro and micro. Why, when you heat a balloon up, does it get bigger and all that kind of stuff? But yeah, it just upset your reading scores. I did some reading, and of course, it turns out if you're going to take a heavy, some chemists will say that atoms do get bigger when you heat them up, but don't.
Yeah.
So,
there's always a discussion to be had on that.
Well, the model gets more complex the deeper you look. But as far as I'm concerned, they don't get bigger. They don't change size.
That's it. So we talk a lot about things like models, and we talk a lot about things like representations as well. And it's mentioned in the book, and it comes up over and over again, especially when we do our chat physics chats on Twitter. People absolutely love the simulations on, I will say PhET, but for those of you who might not have seen it before, it's PhET. So the simulations available on there, which can give you such good visualizations of these abstract concepts, are absolutely brilliant. So James, what do you think about using simulations in the absence of maybe practical work or maybe diagrams?
I'm going to split that question into three, but try and answer it quickly. Right. Some of the PhET simulations, particularly on the particle ones or the balloon rubbing, these are utterly beautiful, transformative things for physics teachers, because what they can show is dynamic kind of microscopic or submicroscopic behavior that you just can't have access to, at the same time as showing the macroscopic phenomena, the balloon sticking to the wall, the lid flying off the thing with the gases. So they become an incredibly powerful tool to allow students to move from the thing they can see to the rules that or the explanations. So absolutely, you know, the world is a better place for PhET, Carl Wyman and those people. You know, we are eternally grateful as a physics education community for them. I think, and you know, if you take the circuit stuff, there's a really nice way where you can turn on the macro micro and see the electrons moving, and we can't have a dynamic model. I think there's a danger in assuming that they can then replace practical work, because I think that's a slightly different argument. I think they serve the purpose. I know in lockdown some people have just taught circuits entirely with PhET and been successful. But I think it's a danger, because if we go back to where we started, one of the things about physics is, let's look at the real world on the table in front of us. Let's look at things, let's poke them, prod them, bend them, squeeze them, throw them, drop them, break them, measure them, look at them, and see if we can come up with a set of rules for how that works. And I think if our experience of physics then becomes completely PhETified, then I think that's a shame. Mm-hmm. But I can see it as being no, I can't see it. It is such a valuable tool. You can't show why when you rub a balloon and then it sticks to the wall. You need that or a version of that. You can never. There are not enough words that you can get into images that you can get into a student's head enough. I mean, take that one. Literally, you don't even need to do a commentary. It's so beautifully constructed that it just becomes obvious in terms of what's going on. So they're really, really invaluable. If you're old school, Walter Fent was around before PhET, that's brilliant. And there's a lot of good sims now that are coming in for more sophisticated stuff. So physics is another place to go. And there's some in GeoGebra. So, because this is the beautiful thing about physics and why it's so mathematical. Is if you've got a mathematical modeling piece of software, you just plug the physics in, get a visual representation, the physics just rolls out. So when you're in simple harmonic motion, you can have a little thing doing that, and then you rotate it, and it turns out it's doing that, and then you rotate it, and it's all the same thing. And then they can see, you can join together those mathematical formalizations in visual form. Yeah. And then when they've got the picture, you can say, now we can take all of these pictures, squash them down in a beautifully efficient way into 5 letters. And these 5 letters will describe everything circling, oscillating, bouncing, maybe 4, I can't remember, but you know.
Absolutely. Yeah. Beautiful stuff. So we're coming towards the end of the chat, and we have a few entries for the book draw. So we'll get that going in just a moment. I'll just give people a little bit of extra time for you to pop your name in. For those
what
of
I'd
you
also say is if you go to Hodder's website, I mean, I shouldn't be saying this, it's probably recorded. If you go to Hodder's website and go on sample pages, you can get the first chapter for free. And that's got all that stuff you're talking about. What is physics? Why do physics? And I think for me, I mean, I would say that because I wrote it with Mark, but you know, the section on learning physics is is a really nice little kind of 4 or 5 pages about ideas of physics. So we will give a book away. Obviously, you should all go and buy it, but you can get that first chapter for free on Hodder's website under sample pages.
Oh, that is wonderful news. Thank you so much, James. Lovely. Well, that makes 4 of us, so we will crack on with the book draw. James, is there anything else that you were really hoping to talk about today regarding the book or physics in general?
No, I just say 2 things. I mean, I co-edited it and I wrote 1.5 of the chapters. What I think is the strength of the book is we got together some of the great and good of physics teachers and physics teacher education to write the chapters. So you've got a really nice range of different voices, different approaches, covering all those things. So, you know, I think one of the strengths of the book is it's not just me ranting about how I should be physics. You get that in the forces chapter, but you get other voices. So I think that's what I'd say in terms of, I mean, not as a plug, but in terms of as a resource for teachers. I think that's what I'd probably want to say. And, you know, fair play to all the other authors. And there are biology and chemistry ones available as well.
Okay. That's brilliant.
So the biology one's out now and the chemistry one will be out pretty soon. So they're kind of a suite. And all of them have been pretty overhauled. So even if you've got your older copies, I would suggest it's worth getting the up-to-date ones.
That's wonderful. Thank you so much for that. Right. Let's take a look at this draw then. Fabulous. Let's go.
It's a sense of excitement.
There we go. Our winner is Woody. Thank you so much for that.
Well done, Woody. Typing name in the chat in the book is the easiest book you've ever got.
Woody, if you would like to DM us on Twitter at @chatphysics, we'll take your details and we'll help to get that book sent out to you. Thank you so much. I do hope you all go out and buy that book. There's just so many perspectives in there, as James says, which is absolutely brilliant. Definitely one I would recommend, along with all our others. But that brings us to a close today. So thank you everybody at home for watching. And James, thank you so much for your time today. Bye-bye, everybody, and we'll see you next time. Bye-bye.
Cheerio.